Okay, so last time we discussed about few more machine learning algorithms. Now, so far we discussed 0R, 1R, decision trees, and also prism algorithms. And we also discussed how those implementations with the WEKA data mining toolkit. So today I'm going to talk about another two machine learning algorithms, mainly nearest neighbor algorithm as well as naive-based algorithm. So let's start. So remember when I started discussing about the machine learning algorithms, I told you like the simple machine learning algorithm works well. And in instance space also, another type of machine learning algorithm. So it based on the idea of rote learning. What I mean by rote learning in this particular case is just remember the training instances. So simple algorithms in this particular area, what happens, you simply store training instances, and though that is the model. So you are not going to learn any model like in previous cases, what we have observed, like decision trees or the rules. But instead, it basically store instances, and then whenever you get a new situation, and when you want to find out what will be the outcome, you look for a similar instances, and then through that you are going to make some predictions, classifications, and so on. So since these classifiers consider the instances themselves, we call it instance-based learning, or sometimes we call rote learning. But then it's an interesting one. We observe this even in our society as well. When you find friends, we can see similar interest, people, students works together. So that's the exact idea in these algorithms as well. So whatever the learning happens in this particular case, it's based on how similar those instances are. So therefore, we are going to find some similarity function, right? Some similarity function. And the similarity function is what we are going to assume that what happens in the learning phase. So then I hope you can understand that there are no, training phase like in all the other algorithms we have discussed so far. Instead, it has a testing phase. So the learning happens later in these algorithms. So therefore, we say this is lazy learning. So if you take machine learning algorithm like decision tree, we call eager learning. Why we are saying eager learning? So it learns some structure in the data based on the training data. But in instance-based learning, what really happens, the learning happens during the testing phase. So therefore, we call it lazy learning. So the methods includes nearest neighbor or in K nearest neighbor. So let's see what those algorithms are. Right. Now, I told you about the similarity function, but if you look at calculating similarities, most common use is called Euclidean distances, right? So that means you are trying to find the geometrical distance between the instances. So that's what generally use. But of course, if you think about, if you have just one attribute, we call one, and then let's assume that you have just numerical attribute. So if that is the case, simply you can check the difference, right? So that's be the simplest case. But we know normally we have multiple different attributes. In that particular case, we have to calculate the Euclidean or geometrical distance, right? But now what about if you have categorical data or nominal data? Like weather data set, we didn't have any numbers. We had some predefined set of values. We had things like outlook sunny, rainy, overcast, and so on. So how do you calculate the distance if you have categorical data or nominal attributes? So in that particular case, what it considers is, if the values are different, we say the distance is 1. If the values are equal, we'll take distance is 0. So that's how you can actually work on nominal attributes. Finally, there's another question. Now remember, we are calculating distances. Then the natural question is, are all attributes are equally important? Why? Because that how important these are is very important, and we can use different weights here. So if you learn like regression, for example, regression coefficients indicates that how important the attributes are. Similar to that, in nearest neighbor algorithm, we can actually apply different weightings so that the higher the weight, we can say more important it is for the final decision. Right. Now, if you take the nearest neighbor algorithm, and the distance function is what we are going to use. And as I told you earlier, we can use the Euclidean distance. So in Euclidean distance, what it does, you take each an attribute. Let's say you have two instances, A1 and A2. Simply, you calculate the differences between individual attributes and then square. And you sum up all the values. That means you sum up all the squared attribute differences, and then you will get the square root of it. So in this particular equation, you can see, we'll assume that we have k attribute. So the first attribute is A1, then A2, and the final one AK. So the two instances we label as 1 and 2. So you get the differences and square them, and you get the sum of the attributes from 1 to k. And then finally, you get the square root of this. Right. So that's the most commonly used technique. But of course, you can take other metrics as well. For example, we have a metric called city block or Manhattan metric. What it does, simply you get the differences and then you get the absolute value. Right. So therefore, now you can see, in this particular case, you get just the simple differences, you will square them and so on. So that means there could be like many more distance measures, right? Isn't it? So of course, you can actually generalize this measure, and this measure is called Minkowski distance. And it looks like this: sum of all the differences to the power of p, and then you will get the 1 out of p. So that you can see, when p is 1, this will map to Manhattan distance, because this is 1. This is 1 divided by 1. Simply you get the differences, absolute value. So that is Manhattan distance. But if you say p set to 2, of course, you take the differences, square them, and then finally you get the square root of this. So this is called Euclidean distance. So ideally, we can use a distance metric to identify what are the attributes or the closest attributes in the data set. Right. Now that we have understood about the idea and how it might use in various different situations, right? So let's look at a simple application. So in this particular case, maybe I will start with this, right? Let's assume that we have 4 points. So points are like this. You can actually calculate the values. So the point x1 is 1, 2, x2 is 3, 5, x3 is 2, 0, x4 is 4, 5. So assume that we have 4 points. So we have x1, x2, x3, x4, right? Then let's calculate the distance among these attributes. These are called dissimilarity metrics, which will be helpful for you when we want to figure it out how close these attributes are for a given data point, right? So shall we start? So we say D, we'll say L1. That means Manhattan distance between x1 and x2. So let's take these two instances. You get the difference, right? So it's absolute value of 1 minus 3 plus 2 minus 5. Which is equal to, this is 2. This is 3. So the distance is 5. Yes, so this is 5, right? So likewise, you can fill the table. Similarly, if you take the Euclidean distance, let's say L2, so you'll take the square plus square, and then you get the square root of this. So that is 2 square, that is 4, plus 3 square, that is 9, the square root of this. So which is square root of 13. So let's take 13 square root of this, which is 3.61. So this would be 3.61. So actually, if you look at like what exactly you want to do is calculating the distance from test instance to all the instances. So let me take this one where this will show you like 2 features. When you have just 2 features, and if you have numerical features, we can plot in the 2D plane. So what you notice is there are 2 classes we have. Class A represented using circles, class B represented using squares. So here we have 3 instances from class A, 3 instances from class B. Right. Now, this gray will actually shows you a new instance. We don't know the label. Now we need to identify whether this gray dot is right, whether it's belong to class A or class B. So it depends on how close it for the instances. So if you're using nearest neighbor or simple nearest neighbor, we say n is 1, right? Here I said its k is 1. If you look at the nearest instances, you see that so this gray dot is close to the class B instance. So what happens if you are going to say, okay, just consider 1 instances around this, then what happens? The output will be class B. But of course, let's say you are going to focus on 5, k is 5 nearest neighbors, 5 nearest instances. Then what will happen? You can notice here, where if you're calculating this, you will see you have 1, 2, 3, 4, 5 instances. Out of 5, you can see 3 circles, which is a majority is 3, and the final output will be a class A. So this is exactly the idea that we actually consider when you are calculating, when you are getting a new instance and when you want to identify you compare, you calculate the distance from the test instance to all the other instances in the dataset. And then what you do, right? You find the nearest instance. If you say k is 1, then you get the nearest instance, and then you take the label from the nearest instance. If you set a higher k value, let's say k is 5, so you find out the 5 nearest instances and then find the majority. So I think now you understood how it works, especially in a classification problem. Classification problem means you have a data with labels. So in this particular case, we have two types of labels as class A and class B. Right. Okay. Now that we have understood about how the classification happens, we need to understand there are some other issues. What are the other issues? Okay, first one. Remember, here we are calculating distances. What happens? The scales are different. What I mean by this, let's say you have one variable, the value goes from 0 to 1. Another variable, value goes from 0 to 100. So you see what happens. When you have a larger range of values, that will affect for the main decision. Therefore, if you're using nearest like algorithm, you need to normalize it. What I mean by normalizing means for all the attributes, you have to put into a same range. Like for example, between 0 to 1. So that means the minimum value should be 0, the maximum value should be 1. So in that way, we can say that the attributes are normalized. So in this particular case, it will show you, right? It will show you the normalized values, right? So attributes are normalized. A1, in this particular case, you take the value, subtract with the minimum value, and again divide by the differences, right? So you have the value, subtract with the minimum, and divide by the mean and max. So you have a max, subtract mean. Okay, let me go back to the data set. Can you apply the minimization for the data set? Let's say we have these two attributes. So normalize this. Okay, the question is like, how do you normalize attribute 1 and attribute 2 given the maximum and minimum, using maximum and minimum? Okay, let me start with just one, and then maybe you can try the other ones. Right, so I'm going to normalize this value, right? So what we need to do is, let's say attribute is AI. We discuss the equation is you take the value, subtract minimum value, then divide by the difference between the max and mean. So that's what we said. So what is the value? So you can observe it's 1 minus. What is the minimum? So in this attribute, the minimum is also 1. Divide by what is max? Max is 4. What is mean? That is 1. So you will have 0 divided by 3. So that is 0. So after normalizing, right? So this value becomes 0. You get my point, right? Yes. Okay, what about this value? Can you give me the normalized value? Okay, last point. So the first one we discussed, when you have different scales, how do you handle it? Remember that you normally normalize this. So remember that when you are using nearest neighbor like algorithms, so you normalize the attribute. So what happens then? The values will be between 0 and 1. Right. The last point is missing values. Now, sometimes when you have attributes, the values will be missing. So how do you handle that? So when you have missing values, remember the policy that we can have is the difference is maximum. So what do you mean by maximum? That is one, right? Yes. So you assume that the value is maximally difference, right? Distinct, what we call it, which means if you have normalized attributes. Right. Just to summarize, how do you handle nearest neighbor? Right. You will notice that although this is instance-based algorithm, it's often accurate but slow. The reason for slowness is basically you have to calculate the distance from the train instance to all the other attributes, and then all the instances, and then you have to find the closest one, right? So if you have large number of attributes and the large number of data points, you will see that it's very, very slow. So one way to handle this is you can have some efficient ways of representing this data. There are some data structures like KD trees or the ball trees, which we can use to efficiently store the distances or the instances details. Next point is you can assume all attributes are equally important. So, so that's an assumption. If it is not the case, maybe you select important attributes or you use weights. What I mean by weights here, if you have like some attributes are more important than the others, okay, use more weights for the important ones. Next, there could be some noisy instances. So we know that in any data set, there are going to be noisy issues. So if that is the case, remember, you use large K value. As I told you earlier, if you have two class problems, you can say the K, the number of nearest instances, as 1, 3, 5, 7, and so on, right? But identifying this is very, very difficult. And the other point is, this is come from the statistics, and this particular algorithm actually used even in early 1950s. Right. Okay. So the next I will show you like how you may apply. So I'm going to select the WEKA. So let me share. Okay, so in this particular case, right, I'm going to select the Explorer. Explorer is useful when you are working with just single data set. And you can work on one algorithm at a time. So let me open some data. So for example, let me take iris dataset. Actually, iris dataset is it's about classifying 4 different types of flowers. I just want to show you like the type of flowers. So let me see whether I can find you some details about this. So this, the data set, you have a very similar flowers, right? Actually, we are going to use this with Python as well. So after I finish the WEKA part, we'll look at it. But let's show about this, right? Okay. Right. Okay. So let me show you from a different one. Here is it look like. So you can notice that in this particular data set, what we have is the main aim is classifying flowers into these three categories: versicolor, setosa, and virginica. And visually, you can see that the flowers looks the same, right? So in machine learning approach, what they have done, they have collected about like information about 150 flowers and 50 from each class. So the measurements are like based on measuring their sepal and petal width together with class labels. So you have four measurements: sepal length, sepal width, petal width, and finally you have a class label. Right. So with that said, let me go back to the data set again. So here is the data set. So when you click edit, I think you can see, you can notice here the data points. You have 150 data points in three classes. And we have four measurements. Right. So the four measurements, we have sepal length, sepal width, petal length, and petal width together with the class label. Right. Okay. Now you can see the three classes. We have 50 instances from each. And then you can see how the data is distributed. So this is numerical data. So therefore, in this panel, what you notice is minimum and maximum and mean and standard deviation values. Right. So that's how it works. So let me go to a classify tab. And then we have to select, like in this particular case, if I'm going to use nearest neighbor, so you have to click it here. You have to go under lazy algorithms, and then IB1 is for simple nearest neighbor, right? So we are using, you can notice normalized. You can click more if you want to need more. Right? Users normalize Euclidean distance to find training instance close to the given test instance and predict the same class as the training instance. Right. I'm going to click OK. And well, I will click and see the accuracy. So in this particular case, you will see we have a classifier. Time to take the build, the model is 0 seconds because I told you, like in the training, we are not building any model as such. But when you evaluating, yes, you calculate the distance from each test instance together with the other training instances. And you will notice here, if you're using nearest neighbor algorithm, you are getting about like 95% 3-3 accuracy. Right. So that's all what we have. Of course, you can try whatever we are very familiar with. Maybe let me check whether we could go for trees, J40. Yes. I'm going to click it. Of course, yes, we are getting better accuracy. Here we got about 95. This is 96. Let me see the visualization. Okay, here is how it looked like. Right. So you can notice how it is classified. You can notice the setosa is easily separable compared to the other two types, right? Setosa, versicolor, virginica, right? And so, of course, you can see this information as well. Um, for example, if you want to see how visual separate these two, you can go and look at visualization. So, for example, if you use sepal length, right, 1 and 3, for example. So it you can see how the three classes separates this. Maybe I can go with so let me try this. Yes, so you can see here. So this visualization shows you how easily we can separable. So the blue lines are setosa, you can see. So the setosa can clearly separable from other two classes. So that's what we have observed. So you can see a blue dots here, which indicates the setosa flower is easily separable from other two, that is versicolor and virginica. So you can see these are overlapping, but this is clearly separable. Right. So you have observed this visually as well. Right. So that's all about the nearest neighbor. So play around the data you have, building different models. So later in the course, I will discuss how exactly you are going to compare the accuracies. Okay, now that we have discussed about nearest neighbor algorithm, so let me start discussing another interesting machine learning algorithm. Right. Before we start, I want to discuss one more idea. Remember, we have used 1R method. If you recall 1R method, what happens? You are going to select just one attribute. You are going to create a single level decision tree to make predictions. Okay, so what we are going to discuss it now is opposite of 1R. That means use of all attributes. So in statistical modeling, especially in naive-Bayes, there are two assumptions we are going to make. The two assumptions are, we assume that attributes are equally important, right? All the attributes are equally important. We have observed that it's not the case, but yes, we are going to assume that, okay, all the attributes are equally important. Second point, they are statistically independent. What do you mean by independence here? We know that when you change a particular attribute, it might affect the other attributes as well. So let's say you increase one attribute. If other one also increases, then we say, okay, we have positive correlation. If you increase one, then let's say the second one decreases, then we can say negative correlation. If it is not that, then we say it's random, right? Okay, so two assumptions, we assume that they are equally important and statistically independent, right? So these assumptions will be never correct, right? So there are issues of this assumption, but if you are implementing this practically, if you are using, you might have observed that this simple probability-based classifiers works really well, right? And that's what we are trying to understand. Right. So correlation diagrams, I have put it here because just to say that, dependence between multiple attributes. So if you have like two attributes, let's say you have numbers, and when X increases, let's say Y also increases, we say positive correlation. When X increases, the Y decreases, then we call negative correlation. And if it is spread evenly among this, then we say no correlation. So one of the assumption is we assume that there's no correlation among the attributes, which is not true. Right. Right. To explain this, I'm going to use the weather dataset. I hope you remember the weather dataset, or let's start sharing the weather data from the beginning, because this is what we need to, understand use of weather dataset. Okay, let me first share with you the weather dataset, and then we'll look at, right. So let me see. Right. Take a screenshot of the weather dataset to start with, because we need this to understand how naive-Bayes algorithm works. Right. Okay. Now, let's see what we are going to do in naive-Bayes classifier. Simply, we are trying to calculate the probabilities, right? Given the class value, we are going to look at how probable is based on the attribute values. So that's what we are doing with naive-Bayes. So the output of the naive-Bayes classifier is some probabilities. And I'm going to explain that with this small table here, right? So you remember that in decision trees, the output is a tree structure. In a rule sets, we have a rules, right? In naive-Bayes, right, the model is these probability values. So let me explain how we are going to calculate the probability values. First of all, let's take one attribute at a time. Take outlook and calculate how many times the class appears given an attribute value. So for example, if you take outlook sunny, if you go through the data set, we observe that there are 5 instances. 2 are classified as yes, 3 are classified as no. Take outlook overcast. Yes, there are 4 instances classified as yes, 0 for no. Rainy, yes, you have 5 instances, 3 yeses and 2 nos. So to calculate the probabilities, we add up everything here. So you have 9 instances and here we have 5 instances. We divide it. So what happens? The probability of outlook is sunny given the class is yes is 2 out of 9. Similar, given outlook is sunny, the probability of classifying as no is 3 out of 5. So likewise, you can actually calculate this. Right, let's try to fill this table because this is what we need to understand first. So similarly, if you check the temperature column, and if you select number of, temperature is equal to hot, so there are 2 and 2. Mild, you have 4 and 2. Cool, you have 3 and 1. So going calculating these probabilities. Here together we have 9. So we'll divide. So this is 2 out of 9. This is 4 out of 9. So this is 3 out of 9. Similarly, this will be 5. 2 out of 5. This is 2 out of 5. So here 1 out of 5. Right. Now a small exercise for you. Fill the table for humidity. So this will be 4. Altogether we have 7. 3 and 4. Then when we say humidity is normal, we have 1, 2, 3, 4, 5, 6. Your normal is also 7. We have just 1, 2, 3, 4. We have 2, 3, 4, 5, 6, right? Yes. So you have a 6 and just we have 1. Right. So then to get the probability values, we divide 3 by 9. We have 6 by 9. 4 by 5 and 1 by 5. So similarly, try with windy. So windy falls how many times? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 falls. So how many yeses? 1, 2, 3, 4, 5, 6. So you have 6 and 2. Can you check? Then true values, we have 1, 2, 3, 4, 5, 6. So how many true? We have 1, 2, 3, 4, 5, 6. So out of 6, how many yes? 1, 2, 3. So we have 3, and then here also we have 3. So this is 6 divided by 9, 3 divided by 9, 2 divided by 5, 3 divided by 5. So you have probabilities, right? And this is the model, right? When you say model, if you're using naive base, this is the model. So you calculate the probabilities. And this is the output. So given a data set, this will find respective probability calculations. Right. I think this is the first one. So let's take a copy of this because we need it. So I'm going to share. Right. We have the data set and we have the table as well. Right. Let's move on. Now, given a new data set, new day, new instance, let's see how we are going to calculate the probability values, right? So let's say we have given a new day we have outlook sunny, temperature is cool, humidity high, wind is true, right? So first of all, you have to get the probability values for both yes and no. Outlook sunny. So if you go here, outlook sunny, you will see outlook sunny. The two values are 2 out of 9 and 3 out of 5. 2 out of 9 and 3 out of 5. So 2 out of 9 and 3 out of 5. This is for outlook sunny. So likewise, you can find temperature cool. It's this. Humidity high, windy true, and this is the proportion of the attributes. So when you say yes, we have 9 out of 40. No, we have 5 out of 40. Right. And then we can actually, find the values. And if you look at the values, these are not probabilities. Why? If they were probabilities, they should be added to 1. So therefore, we normally use the word likelihood. So by multiplying these probability values, the values you are getting is called likelihood of the two classes. That is yes and no. So to find the probabilities, we need to normalize. You get the value, divide by both of them. So probability of class yes is get the value, divide by both of them. Then for no as well, you divide the same. You get the value for no and divide by the total. And these are probability values. So if you closely look at it, these two numbers will add up to 1. So therefore, these are probabilities. So we can say something like this: probability of the class is yes, we can say 20%. No, we have 79.5%. So in this way, we can easily compare using probability values. Right. Now, similar to this, right, I hope this part is okay. Those who have understood up to this point, can you please raise your hands? So we need to find out the values for these 4 attributes, yes? So let me say, so I'm going to find the likelihood of yes. So if you look at outlook overcast for yes, outlook overcast for yes, we have 4 divided by 9 times temperature cool, that is 3 divided by 9 times, then we have a humidity high. Humidity high, we have 3 divided by 9 times windy true, again 3 divided by 9 times the play attribute, we have 9 divided by 14. So this is the likelihood value. But if you look at the likelihood value of no, so outlook overcast, no, we have 0 divided by 9. Right? And then you can check others. But only problem is, as soon as the first value becomes 0, the likelihood becomes 0. When you have likelihood become 0, then you cannot find the probability values, because once it is 0, everything becomes 0, right? Which is the problem in this particular case. So therefore, when you have a situation like this, you cannot apply the same procedures we discussed earlier, because whenever, as soon as this becomes 0, there's no point. Whatever the values comes after this, right? Everything becomes 0, right? So this is known as a special case. What is the special case? Right. Let me clear this for you. So this is known as zero frequency problem. So what do you mean by zero frequency problem? And whenever you have outlook overcast for class no, probability 0. So then you have a 0 posterior probability as well. So therefore, you cannot apply the way we have used earlier, right? So you have to solve that issue. So to do that, what we need to do is you have to replace, right, 0. So there are like many ways that you can handle this issue. But the simplest way to do this is you can add 1 to every count and then you normalize it. This is called Laplace estimator. So what we do, right, in this particular case, you can see for each and every value, we add a 1 and we normalize this. So by doing so, what happens? Instead of 0, now we have 1 over 1 out of 8, which is small, right, compared to the other values. So this is how we are going to handle it. So in that particular case, now we can calculate the values. So instead of 0, we can use the adjusted value, right? That's how we handle when you have 0 frequency problem. Okay, so but before that, let me show you like mathematically how do you do this. So one thing I didn't discuss is, so this idea of calculating prior probabilities and posterior probabilities comes with the Bayes rule, right? So given the evidence, we need to find out the probability of the event H. So H means here it could be yes and no. So evidence in this particular case is the new date. Given the new date, we need to find out the probability of class is yes or class is no, right? To do that, what we do is, given the hypothesis, given that we know the class label yes and no, we calculate the event probabilities. And we'll assume that all the attributes are independent of each other. Therefore, we can simply multiply them together. So that's what we do. And we multiply with the probability of the event divided by the probability of the evidence. So this part we don't know, but we can make use of what is already known. And when you normalize, this part is cancelled out, right? So here we will say the prior probabilities, and then we calculate the posterior probabilities. So applied to the previous example, evidence is our new date. Given the event is yes, what we are supposed to do is, given this new date, we want to find out the probability of class. The play is yes. So how do you do that? For each attribute value, given the class is yes, we find out the probability values. Since we have assumed everything is independent to each other, we can multiply probabilities, and then finally we multiply the probabilities of the event yes divided by the probabilities of the evidence. So this is unknown, but we have this. So similarly, if you do the same for class no as well, and when you normalize, so this part, probability for the event, will be cancelled out. And that's what we have observed in the previous case as well in the calculations. So we don't know the probability of the evidence, but then it doesn't matter. When you normalize, that part, cancels out. Okay, so that's exactly what we need to discuss. So we have observed that, okay, how do you handle when you have 0 values? Okay, what about the missing values? Now let's look at an example. How do you handle missing values in this particular case? So if you have missing values in the naive-Bayes classifier, so you don't include the instances, right, in the combination. And when it comes to classification, you omit the attribute from the calculation. Now, to explain this, let me take a new data, a new date. And in this particular case, let's assume that we don't know the value of outlook. And let's say we know temperature is cold, humidity is high, wind is true. So what we do is when we calculate the likelihood, we will omit, right, this attribute. And then you calculate the likelihood and the probabilities for the remaining. So therefore, the very first value is represent the temperature cold. We ignore this one. For yes is 3 out of 9, no is 1 out of 5, humidity is 3 out of 9, 4 out of 5, windy, we have 3 out of 9 and 3 out of 5. Finally, play, it's 9 out of 14 and 5 out of 14. So we'll get the likelihood values. Normalize it, you will get about like 41%, and the remaining will be 59, right? So that's how you calculate the probabilities if you have missing values. Right. Okay. So we discuss that part. Okay. Now, last part. Now, what we have discussed so far is where you can calculate the probabilities. When you have labeled data, nominal attributes, we don't have any issues. But what if you have numerical data? Okay, let's assume that we have a new situation now. So what is the new situation? Let's say we have numerical data now. So in this particular case, you need Outlook, we have nominal data, that means labels. Windy also we have nominal data. But for temperature and humidity, we have numerical data. So if you have numerical data, what you need to do is, right, we have to way of calculating probabilities, right? So let's see how we can do that. So when you want to find out numerical attributes, first of all, we are going to assume the attributes have normal or Gaussian probability distribution. So that's the first thing. And then we are going to find out the density function. So given we know the sample mean mu and standard deviation sigma, and the equations are given here, right? We can define the density function of fx as 1 over square root of 2 5 sigma e to the power minus x minus mu square divided by 2 sigma square. So what it means, given the data set, let's say we have the two data sets. So two values. What are the two values? Temperature is 66, right? So what we do is you go back, right? And then we apply the equation. So for that, what we need to do is, for temperature, we have to separate out the values based on the class label, right? If you separate out this, if you get the mu and then the sigma, it looks like this. So mu is 73 and sigma is 6.2 for class yes. For no, the mu is 75, sigma is 7.9, right? Given the class label yes and temperature 66, we need to find the probability distribution function. 1 over square root of 2 5 sigma. Sigma is 6.2 e to the power minus, right? The value is 66 minus mu square divided by 2 sigma square, which will be equal to 0.0340. You can check the answer. Similarly, you will find the humidity is equal to 90 given yes. You can apply the same and calculate the probability values. So now, given our new day, let's look at how we are going to calculate this. So we have probabilities, right? These are also going to get as probabilities, although they are density functions. And when you normalize, right, for this particular day, we are getting 20% 9 for class yes, 79.1 for class no. So what is the final outcome? Okay, the final outcome is, as you can see, we will observe that given the class yes, the probability is 20.9. No, it's 79.1, right? And that's how we calculate when we have numerical data. Right. Now, if you ask me like why probability densities, so probability densities can be go beyond one. So they are not actually probabilities, right? So but if you look at the approximate relationship between the probabilities and density, it's a fraction, a very small fraction from that. So that is sufficiently small. So therefore, when you calculate the likelihoods, you can use density. So that's how we will actually use these values when you are calculating probabilities. Right. Okay. So that's about the naive-Bayes classifier. Just to summarize what we discussed, we had two assumptions. We assume that all attributes are equally important and they are independent each other. And so the outcome of the naive Bayes is simply a table of probabilities. And when you get a new test data set, you calculate the probability values, multiply them, and then you normalize it, right? And that's how we work with naive Bayes. Another difference would be instead of just outputting just one class for all the other machine learning algorithm, this will give you probability values, right? So both classes, it will give you probabilities. So that's another difference. Okay, one final part in the naive Bayes classifier. So there's a variant of naive Bayes which is very popular in text domain. What I mean by text domain, in text classification or natural language processing, this is very, very commonly used classifier, multinomial, right? So in text data, we have a bit of a problem. So to apply machine learning, all the data, you have to have a set of rows and the columns, right? Row is the instances, column, right, represent all the attributes. So to represent this in a matrix form, which is what we expect machine learning, right? We normally can use how word appears in the document, right? And then we can calculate the probabilities. But one more thing, when you calculate the probabilities, you calculate, right, the frequency of this. And this is why we call multinomial naive Bayes. So it will actually consider the frequency counts, how many times word appear in the documents. Right. Now, let me briefly discuss how they calculate the probability, slightly different from how we calculate probabilities for the naive Bayes. So to explain this, we are going to make some assumptions. We are going to assume that we have two words, yellow and blue, and the probabilities are like this. You have a 75% for yellow and 25% for blue. So that is the word appearances. But if you take a document, you might have multiple values. Now, in this particular case, we have three documents. We have we have three text in the document. We have blue, yellow, blue. So what we need to find out is, given the hypothesis, we need to identify the probability of blue, yellow, blue. So if you apply to the previous equation that we have discussed, right? So we discussed the number of words in this case multiplied by probability divided by the numbers. So in this particular case, you will notice we have 3 here, and the probability is for yellow it's 75 divided by 1. It's factorial. And then second one, blue, again the factorial, right? And then you multiply everything and you are going to find the probability values. So in that way, we can identify the likelihood of word blue appearing multiple times. So what you need to understand here is it will actually consider the frequency count of the word, which is very, very important. So in this particular classifier is quite commonly used in text classification problem, especially classical machine learning part. Okay, so that's all what I have about the naive-Bayes classifier. Let me now show you this in WEKA. So I'm going to open up a WEKA again and a data set. So let me open up a simple weather nominal. So in nominal, we have counts. We can go to classify. And then here we can go to Bayes. And then we can select naive Bayes. Right? And when you click it, so it'll actually, you can find out. So as you can see, in this particular case, what we have observed is just probability values, right? So this is the right. So in this particular case, we have probability values. So you can see for the class yes and no, it will calculate the number of counts, right? So you can see the number of counts here. So like I said here, since it becomes 0, it will actually add 1 for each, right? So you can see the counts is added. So in that case, to avoid the 0 frequency problem, count is added. For all cases, you can observe, right? Whenever there was a 0 frequency problem, right? 1 is added, right? So you can observe that. And that's what we are going to do. And these are the values that they have considered when it comes to probabilities. Similarly, let me open up another data set. Let me open a numeric data set now. You can notice temperature and humidity, they are numeric attributes. So let me use the same naive Bayes, right? You can see here, if you focus here, right? Simply they will calculate the mean and standard deviation so that they can apply to probability density functions to calculate the probability values. And that's exactly what we have discussed in the theory. Right. So that's all we have for today then. Right. So first of all, we need to understand how we are getting or evaluate machine learning algorithms. So what we have observed so far is just we select machine learning algorithms, we build them, we observe them, right? So there are many others. So, but I have actually select one from each at least. Up to now, I have selected one from trace. We discuss ID3 and J48. Under rules, we discuss Prism. And lazy, we have discussed IB1. And the base, we have discussed naive base. And also I have discussed a little bit of a naive base multinomial, right? But there are others as well. Okay, that's the first part. The second part is we need to understand various test options. What I mean by test option is, like, given a data set, right? We are going to build a model and we have to identify how good our model for new data. And that's exactly we are trying out here using different test options. Right. Let me show you this. So I'm going to open up from the beginning, right? I'm going to start with the nominal data set. We have weather nominal, right? And I'm going to go to classify tab. So let me see. We can start with the very simple one. Let me take, for example, 0R. So what is 0R, right? We know that we get the majority. So I'm going to show you with the test option. Use training set means you build the model using the training and test with the same data set, right? And this is what will happen. 0 is predict the class value, yes. Evaluate on the training set, right? We have given as 64%. The second one is we can split the data set as training and testing. So what it means, you divide the data set 2/3 for training, 1/3 for testing. 66% means ideally you are taking 2/3. You divide the data set into 3 parts. 2 parts you take as a training and 1 part for testing. So what you do, you build the model using 2 parts and then you test using 1 part. So if you click yes, now you can observe, right? So earlier we have 64% accuracy, but as soon as we got the percentage split, it slightly go down. And this is okay. Why? Because this will evaluate the same data set, whereas here you separate the data set. You separate the data as training and testing. You build the model on the training and evaluate on the test set. Third point, this is what we have done already. We call cross-validation. So under the cross-validation, what happens? It divides the data into 10 parts. Take 9 for training, 1 for testing, and you repeat for 10 times because you are separating data for 10 parts, right? 1 part each you take out for 10 times. So this will be the most, one of the best ways to do if you use a cross-validation. You run this for 10 times and then you average out, right? So that's what we have done here as well. Okay. Now let me show you another. Let me use 1R. Okay, if you use a training set, you will notice about 71% accuracy. Percentage split, okay, goes down to 40. Cross-validation, you'll get about 42%. So you observe that if you're using a training, you are getting very high accuracy. But when you're using percentage split or cross-validation, it's low. So you can see that, right? So what we need is we need high value with these two. And you should never use the training data set to evaluate your models, right? Maybe we can try with a large data set. Maybe I will open up another data set. Iris data set, we have 150 data points, right? Okay, let me select that one. Okay, so we'll select, for example, trees. Okay, let me use trees. I'm going to select J48. So J48 with Iris dataset, right? Let me use a training dataset first. I'm going to click Start. Okay, you might see that, okay, our classifier is 98% accuracy. You might think that, okay, this is very accurate. No, the reason for this is you build the model and you use the same data to evaluate. Evaluation in this particular case, what I mean by this is how good it is when we evaluate on new data. But when you use training data, you will get very high accuracy. So you should not use this. Okay, let me show you this with percentage split, right? It's about 96. Let's do the cross-validation, right? Slightly low, but you can notice that, okay, constantly it will give you very high accuracy. So this is observation you should meet, right? If you are the classification is really good, you should get a decent accuracy with cross-validation. Right. So let me use another example. What about nearest neighbor? Let me use training set and click Start. Okay, this is really interesting. Why we are getting 100%? Remember, I told you there's no training, right? We take all the instances themselves. And if you are trying to test using the training data, this is a perfect accuracy. But you will see what happens when you use percentage split. That means you split the data as 2/3 for training and 1/3 for testing, right? Goes down to 96. Cross-validation, so it goes to 95. So most of the time, if you have like small data set, you can evaluate using cross-validation. But if you have a huge data set, like millions of records, maybe this might not be practical. So, sorry, cross-validation might not be practical. Then you can go for percentage split. But never use the training data set. Okay, let's try with the naive base as well. I'll start with the training data. Okay, we got 96 percentage split. We got 94 cross validation. Okay, got 96 again. So you see the importance of selecting test options. Okay, actually, if you are comparing as what I have done with multiple classifiers for a data set, you don't have to do it one at a time. So let me explain efficient ways of doing this. So to do that, I'm going to close the WEKA Explorer. Right. Now go to Experimenter. So Experimenter is really good. If you're going to experiment with multiple data sets and multiple machine learning algorithms. So if that is the case, go for Experimenter. So let me show you how to use Experimenter now, right? And then, okay, the interface is slightly different now. Here we have three tabs: setup, run, and analyze, right? So I'm going to say click new experiment, right? And then we have to decide, right, what are the data sets that we are going to use and so on. So I'm going to start with the classification, and I'm going to use cross-validation. You can see here, I'm actually selecting, it's automatically 10-fold cross-validation. So I'm not going to change anything here. And it'll actually repeat for 10 times. So I'm going to select a data set first. I'm going to add, okay, the iris data set. Right. Next, I can apply several algorithms. So let me start choosing 1R, the simplest one, right? Let me select decision tree. I'm not going to change any of the parameters. I will talk about these parameters later on. And then we'll go for nearest neighbor. And then we can go for naive Bayes. So you can notice that this side we have one data set, we have 4 algorithms, right? We have 1R, J48, that is decision tree. This is IB1, that is one nearest neighbor. And finally, naive Bayes. Okay, now once you actually set up this, I will explain one more time. You start with clicking new and adding the dataset, clicking add new and the iris dataset, then adding new, and then I'm actually selecting 4 algorithms. So once we finish that, we can go to run tab and click start. And what you notice here is, what happens is take the dataset, run through all the 4 machine learning algorithms. So it started, right? And quickly stop as well. And it says there's no errors. So once you finish this, go to Analyze tab. Again, theory I will discuss. And click Experiment, meaning like I'm going to get the data from experiment to analyze. And then I'm going to use t-test. And then we'll perform test. Right. So what happens here, we actually use iris dataset with 4 machine learning algorithms. We repeated the 10-fold cross-validation 10 times. So you have average data. And we are comparing average this using paired t-test, right? So you select this. And then what we observe here is, so algorithm is compared with all the others. So the first one we have selected is the 1R algorithm. And in this particular case, what you notice here is 1R accuracy is compared with others. Right. Now, in this particular case, what you observe is compared to the 1R accuracy, whether there's a significant difference between the accuracies. So initial accuracy is about like 92%. Trees, it's about 94. Nearest neighbor, it's 95. Naive Bayes, it's about 95.5. So this will actually indicate the best and worst cases. And the middle one means there's no significant difference. So here also there's no significant difference. But if you look at here, if you compare knife based accuracy with the 1R, actually this indicates that there's a significant difference between accuracies. So as you can already see that we are comparing the average data. Using that, we calculate how significant those are. So in this particular case, what we are going to observe is compared to 1R algorithm and the base. So there's a significant difference in accuracy. So the base is better than 1R. Of course, if you just look at the accuracy number, you might say the tree and the nearest neighbor is better than 1R. But you cannot statistically say there's a difference between there's a difference there's a difference among these machine learning algorithms. Right. So that's about how we can actually perform experiments comparing a particular algorithm with the others and trying to identify which algorithm best for your problem. I think with that, we can finish for today. And the next week, I'll talk about the theory about calculating various different numbers that I talk about this. And then I will revisit. For the time being, I want you to get familiar with the experimenter interface. Try with the existing data and by selecting several attributes and compare your findings. Okay.